Welcome to Voltage Drops. Set up a series circuit here in the DC circuit simulator, and also while you're at it, check the voltage on your battery. My battery seems to be set at 9 volts, which is pretty dopey because it looks like a 1.5 volt battery from the side. I don't know, maybe it's a 9 volt battery on its side. Check the resistance on your resistors, slide the slider around, watch the colors change. You should be getting 3 different resistors. And once your circuit is flowing, once your current is flowing in your circuit, tap in, measure the voltage drop across each resistor. Write it down. Ooh, why is it negative? Well, it's negative because you've got your red prong on your low voltage end. Red to high voltage, black to low voltage. That's industry standard. There. That's better. Write it down. Again, black, low voltage, red, high voltage. Otherwise, you'll get a negative, won't do the meter any harm. Write your 3 numbers down. Then add them all together. And what do you see? Seriously, if you haven't added them all together yet, add them all together now. You should notice that the total voltage drop in all 3 resistors is equal to the total voltage of the battery. This makes perfect sense if you think of voltage, or EMF, electromotive force, as potential. That's what it is. It's electric potential. Well, your potential $90 of spending is going to be divided between all the things you have to spend it on. The parking, the tickets, the swag. All those together, add all them up, they're going to make the $90 in your wallet. If they don't, then you're going to have a hard time paying for that last thing you write. The formula for voltage in a series circuit is the same one that you took notes on yesterday. V1 plus V2 plus V3 equals the total voltage. In a series circuit, the voltage is shared through different devices. You noticed here we had 2 big resistors at 4 something volts each, and then a little one here that was only taking the last few fractions of a volt or so. Bigger resistors use more voltage. They have a greater voltage drop. Let's set up a parallel circuit. Let's ratchet up this voltage to something more interesting. Let's make this a 12 volt car battery. There we go. Okay, now we've got a parallel circuit. Again, black to black, low voltage. Red to red, high voltage. What do we see? Ooh, 12 volts. And what about this one? Again, we don't disconnect the circuit, we just tap it. Oh, 12 volts again. What do you think the voltage drop is going to be on the last one?
12 volts.
12 volts. What do you notice about the voltage drop?
Nothing.
Literally nothing? 0 volts?
It's 12 volts on all of them.
Oh, 12 volts of the battery has a private line here, and a private line here, and a private line here. How many of those resistors do you have to go through if you want to get from the high voltage end with the copper top to the low voltage end that's flat? You could go this way, or this way, or this way. Do you have to go through all 3 at once?
No.
So how many of you do you pick?
You pick one.
You pick one, so you get to drop all 12 of your volts just in that one. Just in that one, you get to drop 12 volts, and that's why they all have a voltage drop of 12 volts. Although you notice that the current is clearly flowing faster where there's lower resistance, and it's clearly flowing much slower where there's higher resistance, but the voltage drop is the same throughout. This goes along with the analogy we were talking about, where the circuit is a Bears game, and each of these resistors are gates in. Yeah, there may be a long line here with 73.5 people, and a medium line here with 69.5 people, and a short line here with only 10 people, but when you get to the front of the gate, you will pay the same ticket price at the front of every gate. Yeah, $12, that'll be the day, more like $120. Make it like the front row seat of Hamilton, you have $1,200, but either way, your $12, your 12 volts, it's the same in every gate. The current may be higher or lower, but the voltage drop is a parallel circuit is the same everywhere. V1 equals V2 equals E3 equals the total voltage because In the parallel circuit, one total voltage drop controls everything. It's the current that's split up through all the different branches, whereas in the series circuit, like we had before, one total current controls everything, and it's the voltage that's shared throughout all the different devices. How can you tell what current is going to be in each branch besides, well, going in and personally measuring it? This is an ammeter here, so you're going to have to disconnect the circuit. If you want to measure the current right here, you're going to have to put the ammeter right here and use the ammeter to fix the break that you made. There's 0.17 amps. That's a medium-sized current. What's our high current going to be here? That's going to take a lot of deconstruction and a lot of reconstruction. Bridge that gap. Oh, bridge that gap. Bridge that gap. There we go. Ooh, high current. Well, 1.2 whole amperes. Well, that would definitely be a higher current. And get that out of there. Fix that junction. Or if you want to measure the total current, well, total in this case means battery. So let's put this ammeter right by the battery. Oh, well, apparently most of the current was going through the 10 ohm resistor, but we still got an additional 0.34 amps coming in from these two to make the total. How can you tell? In advance, use Ohm's law. I1 equals V1 R1. V1 was 12 volts. R1 was 10 ohms, so 12 volts divided by 10 ohms, there's the 1.2 amps we had. Now, go back to the lecture notes you took from yesterday and draw arrows to show the current. I've recently discovered this marvelous little checkbox that says values that I should have been using for the rest of the unit. Show the conventional current instead of the electrons. Draw those arrows, big thick ones for the total current. Show this branch, branching off, and see if you can figure out what the current is that flows here. It's not exactly branch 1. It's not exactly branch 2. All right, this one's easy. This is branch 3. If you go this way, you're going to branch 3. But what about here, in this wire here? If you had to put an ammeter in here, what would you get? And how would you know? Use those arrows and see if you can get some formulas talking about the total current, which was 1.54, and I1, which was 1.2. See if you can figure out what kind of current is going through here. If the values in the simulator bear you out, you're doing it right.